Andreas Venzke from DTU. So he's a PhD student at the Center for Electric Power and Energy. He obtained a master's degree in Energy Science and Technology from ETH Zurich, and his research interest is power system operation and uncertainty, convex relaxation of the AC optimal power flow, machine learning in power systems. So Andreas, you can start.
Yeah, thank you, Ricardo, for your introduction, and hi and welcome to everybody out there. The title of my presentation is Efficient Creation of Datasets for Data-Driven Power System Applications. And this is joint work with Dan Molzahn from Georgia Tech and Spyros Chatzivasileiadis from DTU. The outline of my talk is as follows. First, I will motivate the topic and define the scope of our work. And then I'll be looking at infeasibility certificates and the algorithm that we propose to create data sets. And then I'll be talking a bit about the characteristics of the data sets that we have obtained with our algorithm. And finally, I'll provide some conclusions. So as we have heard before, machine learning has been applied in a range of applications in power systems. And the recent advances in deep learning, such as the success of Go, the success of AlphaGo in the game of Go, have sparked a renewed interest for data-driven power system applications. And one particular application we're looking at here is machine learning for power system security assessment. So power system security assessment is a highly complex task where the system operator screens a large number of operating points with respect to static security criteria, such as the N-1 security criterion and operational constraints, and dynamic stability criteria, such as small signal or transient stability. And one recent application example includes convolutional neural networks to predict N-1 security and N-1 security and small signal stability. And both of these works show that convolutional neural networks are 2 orders of magnitude faster than conventional approaches at these tasks and also have a high classification accuracy. But one barrier to their application is that the performance highly depends on the dataset quality. So if we only rely on historical data, then we only have a very limited information content on abnormal situations. And those are usually the ones that we want to identify with system security assessment. And also the problem dimensionality is very high. So the operator has a large number of control variables and also has to consider uncertainty from renewables and stochastic loads. So in order for a satisfactory machine learning performance, we require balanced data sets of secure and not secure operating points with a detailed description of the security boundary. And this task of creating such a data set is computationally very hard due to the large input dimensionality. So for example, if we look at creating a data set for a 162 bus system or a 1 megawatt discretization interval and 1 loading level, then this would require us to evaluate 10 to the power of 29 operating points, which is intractable. So in literature, there are 2 main directions that have tackled this problem. The first one is importance sampling, where we have subsequent rounds of sampling where we bias the sampling towards regions of interest. This can be, however, challenging. As we will show later, the input space, so the possible operating space of power systems, is largely unbalanced. So that means that actually only a small fraction of that space corresponds to a secure operation. And the second line of work has used composite approaches or Wien copulas to enrich historical data. This, of course, is highly dependent on the quality of the historical data. And the approach that we propose here is modular and parallelizable. It uses infeasibility certificates to classify large parts of the input space a priori as not secure, and is able to obtain a detailed boundary description and balanced data sets. And it does not rely on historical data, but it can leverage historical data during the dataset creation. So now moving to the infeasibility certificates. So first, an illustration of the task that we're looking at. So we have an input space, capital D of dimension D, for which we want to obtain a balanced data set that characterizes the boundary of the secure space. So we can see the non-convex secure space here. And just to put the input space into perspective, so for example, if the operating point is characterized by the active generation set point and voltage set points, then this possible operating space is characterized simply by the minimum and maximum operational limits on these quantities. And a prerequisite for the assessment of dynamic stability criteria that have to be satisfied for the secure space is feasibility to static security criteria, such as the N-1 security criterion and operational constraints. And these static security criteria are described in the AC optimal power flow problem. So we can see here in black the AC feasible space that includes the secure space. And now in the next step, we look at convex relaxations of the AC OPF problem. These enclose the AC feasible space and can provide infeasibility certificates. So if we have an infeasible operating point, x hat, we can compute the closest feasible point, x star, that is feasible to the convex relaxation of the AC OPF. And we do that by solving a convex optimization problem, where we minimize the Euclidean distance from x hat to x star, subject to x star being feasible to the convex relaxation of the AC OPF. And then Molzahn has shown in previous work that you can use hyperspheres as infeasibility certificates with a radius r star. So because we solve a convex problem, we have the guarantee that there doesn't exist any operating point inside the hypersphere that is actually feasible to the convex relaxation, and as a result is part of the secure space. And here we propose to instead use separating hyperplanes as infeasibility certificate. So we show in the paper that if we have operating points that are on the left-hand side of this hyperplane, then those are also guaranteed to be not secure. And what we observe is that if we have multiple hyperplanes for different starting infeasible operating points, then these form a convex polyhedron. And the benefits of the hyperplanes compared to the hyperspheres are that a larger part of the input space is classified as infeasible, and we also have efficient methods available to sample from within a convex polyhedron. And this motivates us to propose an algorithm to minimize the unclassified input space. So this is equivalent to the task of minimizing the volume of this convex polyhedron using an upper limit on the number of iterations. And we just start by initializing this unclassified input space as the rectangular box that we have seen in the beginning. So we simply use the minimum and maximum limits on the from the operational constraints. And then, as long as we haven't reached the upper number of iterations, we sample from the current description of the convex polyhedron. And for the sample that we draw, we compute the closest dispatch that is feasible to the convex relaxation. And now, if the distance from the sample that we drew to the feasible sample is larger than 0, then we add a hyperplane and further reduce the unclassified region. And we return now to step 2 and repeat this procedure until we reach the upper number of iterations. And now I would like to show a comparison of the infeasibility certificate. So throughout this presentation, we use a reference normalized volume of 1. So the possible operating region is characterized initially by a box that has a normalized volume of 1. And using Volesti, which is a C++ toolbox, we approximate the volume of a convex polyhedron. And for the hyperspheres, we use rejection sampling to approximate the volume. And here we can see the unclassified volume versus the number of iterations of the algorithm for a 39 and 162 bus test case. And we can see that the hyperplanes reduce the unclassified volume substantially compared to the hyperspheres. And just to put the number into perspective, so a volume reduction from 1 to 10 to the minus 5 implies that in expectation, we have to draw at least 10 to the number of 5 random samples to identify one potential feasible sample. And this illustrates the point that out of the possible operating region, only a very small fraction actually corresponds to the secure space. And now we move to the efficient algorithm to create data sets. So the goal again here is to create a balanced data set that characterizes the security boundary. And we start off by tightening the bounds for the ACOPF problem so that the convex relaxation that we use afterwards are tightened. And then in the second step, we directly tighten the input bounds by maximizing and minimizing X subject to the constraints of the convex relaxation. And this allows us to initially reduce the volume to B superscript BT. And then in the next step, we run the algorithm where we create the convex polyhedron that characterizes the unclassified input space. And this convex polyhedron has a volume of VHP. In the next step, we draw and classify a number N2 samples from within this convex polyhedron. And now we would like to obtain a detailed boundary identification. And how we do that is that for each of the infeasible samples that we drew in the previous stage, we identify the closest secure operating point. And here we focus on static security. So that means we solve a non-convex OPF that minimizes the distance to the feasible solution to identify the boundary of the secure space. We have also another work where we looked at dynamic security, where we use directed walks using sensitivity measures to traverse the possible operating space towards the boundary of the secure space. And then in the next stage, we fit a multivariate Gaussian distribution to the obtained secure samples and, if available, historical data of secure samples. And then we bias the sampling towards inside the secure space by multiplying the covariance matrix with a factor smaller than 1. And the idea here is to both characterize the security boundary and obtain secure samples. And finally, to do that, we draw and classify a large number N3 samples from this fitted distribution. And the overall algorithm is parallelizable and modular. So in the different stages, we can also, for example, include important sampling or Wien copulas as well. So now going to the simulation results. So first of all, we use the QC relaxation as a convex relaxation because it represents a good computational, good trade-off between the computational speed and the tightness of the relaxation. And we use two existing bound tightening techniques. So the first one is an analytical and the second one an optimization-based bound tightening. We consider two security criteria. The first one are the operational constraints defined in the ACOPF problem. And the second one is the N-1 security criterion and uncertainty in generation and loading. We evaluate the first security criteria on 13 PGLib OPF test cases, up to 500 buses and an input dimensionality of 125. And the second security criteria we evaluate on a 39 and 162 bus test case, where we consider 5 line outages, 5 uncertain loads, and 3 uncertain renewal generators. And in terms of sampling sizes, we progressively increase the number of samples. So in order to construct the convex polyhedron, we draw 1,000 samples. For the next stage where we do the boundary identification, we draw 10,000 samples from the convex polyhedron. And then finally, we draw 100,000 samples from the fitted multivariate Gaussian distribution. And now I want to show some results from the different stages. So in the first stage, we look at the unclassified input volumes for the PGLib OPF test cases. So here for the first security criteria, I show 3 illustrative test cases and the median over 13 test cases. And for the second one, I show the 39 and the 162 bus test case. And we can see that the bound tightening, so here's the volume of the bound tightening with respect to the initial normalized volume of 1, we can see that it allows, the bound tightening allows to a priori reduce the unclassified input space, and that this reduction is test case dependent. And now looking at the volume of the convex polyhedron, we can see that this part allows to significantly reduce the unclassified input space for all 15 test cases. And then in the next stage, we do the boundary identification. And here I show the share of secure samples. So we can see that by directly sampling from this convex polyhedron that characterizes the remaining unclassified input volume, we're actually able to identify secure samples. And also in the next stage, where we sample from this fitted multivariate Gaussian distribution, we can also again capture a good amount of secure samples, leading to overall balanced data sets for a range of test cases. And with that, I would like to conclude with saying that in this talk, I've proposed feasibility certificates using convex relaxations based on separating hyperplanes. And I introduced an algorithm that allows to a priori minimize the unclassified input space. And we have seen that this allows to significantly reduce the volumes ranging from 10 to the -2 up to 10 to the -40. And I've also introduced a modular and parallelizable algorithm that can create balanced data sets with a detailed security boundary description. And we plan to soon release an open source implementation, also including dynamic security criteria and data sets. And with that, I would like to thank you for your attention, and I'd be happy to answer any questions. Thanks.
Thank you, Andreas. So you already have one question here. So the question is about how this behaves with a very smaller space of feasible solutions. So did you try very extreme cases where the space was really small of feasible solution?
Well, so if we go and look here at the volume reductions, then I think the most extreme case was the case 300. So we can see that for the case 300, so the reference volume is 1, and then the volume of the convex polyhedron after sampling 1,000 samples to characterize the unclassified, to reduce the unclassified input space, we can see that we reduced this volume to 10 to the -40. That means that if you would just uniformly sample from the unit cube, then you would have to draw 10 to the 40 number of samples to potentially have one sample that is secure. So that shows that brute force approaches where we just, especially because this case is very high dimensional, if we just brute force uniformly sample from within the operational constraints that are defined in the ACOPF problem, then we will not be able to identify actually secure samples. I hope that answers the question.
Okay, thank you. So another question is about what you mean by balanced database. So can you be very quick in answering that?
Yes, so we want to create data sets for classification tasks. So meaning using, for example, convolutional neural networks to classify operating points as secure and not secure. And with balanced, we mean that the data set should be composed of roughly the same amount of secure and not secure samples. And the underlying reason for that is that it has been shown that this improves classifier performance.
Okay, so it's not related with the balance grid it was mentioned before.
No,
so one last question. Is it possible there are multiple polyhedrons and your method is choosing just one of them?
Sorry, could you repeat that?
Is it possible that there are multiple polyhedrons and your method is choosing just one of them?
No, because the convex polyhedron, the construction of the convex polyhedron relies on convex relaxations. And by solving these convex problems, we get provable infeasibility certificates. That means that when I've shown the hyperplanes, these hyperplanes, we have a proof in the paper that these hyperplanes will never cut off solutions that are actually secure. Because of the nature of the convex relaxation that is guaranteed to include all solutions to the non-convex original problem.
Okay, thank you. So thank you for your presentation.